Hey everyone. So last time we talked about uh, looking at recurrent networks. So today, and then at the end of that lecture, I talked about how we can relate what we did there to photonics, or even, just optics, right? Not necessarily, I mean, photonics is. so So we can relate it to just pure geometric optics, right? So what I want to do now is just show a basic principle of that. So physically, so remember we said that for a neural network, it's just we have an input. That input gets transformed by some activation function to give an output. And then if you have a deeper neural network, you just keep redoing that. The output becomes the input to the new one, recursion, right? So what you're seeing here is I just have two glass vials, right? These are just glass vials that I got out of, it's one of those wall plug-in things for scent. And I just emptied them out and now I have two glass vials, right? So we know from our physics that when light changes medium, when light is propagating from one point to another and it goes through a change in the medium for the permittivity, then the angle that the light propagates through that changes, right? So and then from there you have your Snell's law and everything else, right? So if we have a light source, like a laser, basically it's just going to go in a straight line, right? But if I put something into it, but the glass isn't going to be enough to really bend that light so that you notice too much on where the source is on my hand. But if you think about, like, if you've ever seen straw in a glass, right, you can see the straw bends, right? So we know that that's happening. In fact, it's happening a couple times because it's not solid glass on the inside. But what I can try to demonstrate is I flipped this upside down just so, because the glass is a little bit less weird at the top, so I can get a better demonstration. So basically, if we put incident light, so basically you can see that the laser, I'm not really getting a good long focal beam, and that's because I need it to scatter better, but anyway. You can see that if I hit the glass tube, you can see some of the emitted light being on this side, right? But if I was to move this, and I'm sorry that the beam is dying a little bit. Okay, so here, I don't know if the camera's picking it up, but you can see some is reflected at this point, some is transmitted at this point. This is acting as your activation function. You can basically wrap this up into a whole bunch of math and just call it your activation function. And we'll walk through that math eventually. But the point is that I can take this light, and maybe if I actually do it this way, you can actually see a nice clean straight beam here. If I right about there, and now if I change this, you can actually see the direction of the beam changing, right? So if you imagined a curve that was being drawn on the table, this is going to look so bad. I'm going to try it. I'm not sure if you can actually see, but this book got a Gaussian function. So this is really not going to work out, but I just want to. Okay, so we can talk about a straight line so that it goes along that straight line on our graph, but that's not the actual function. The actual function is this Gaussian, right? So what I want to do is I want to get my light to actually rotate up, and I don't know if you, right there, right? So the light, I didn't change the angle of the light, I changed the angle of the glass, right there. Now the glass is appearing at the top of the function. The light is appearing at the top of the function. And then I could take a second node, and this is so not going to work, but I wanted to try. And the light's too diffuse because the battery in my laser is dying. But you can... Yeah, you're not going to be able to see it on the screen. The point is, what I was trying to do was get the light to leave here and enter in the second glass, as you can see here, and you now have two different ways to change the light. So I could, if my input was fixed, I could steer the beam with this one to some direction and then steer the beam back with this one into a different direction. That's optics. That's geometric optics. That's the basis of basis functions, right? That's the basis of what we're going to do. So now comes the question: is like, I did it very poorly there, right? But the question is, can you actually do a curve fit using light? Can you actually use this to learn? And so when I was using this and I was turning this to get the light to be at the right angle, I was the one doing the learning. The glass wasn't. That's the difference between a neural network. A neural network, the actual glass learns, right? In a real optical neural network, the nanophotonics, that's what's actually getting to. Is the glass, not the way that I'm rotating the glass, but the actual glass is the thing that, and we'll talk about that and how we can set that up through a whole bunch of different means. But the idea is that basically you're sending a signal through the glass that's perturbating the glass. The glass then changes as it heats up with the signal passing through it, and that's charge dynamics and a whole bunch of other cool stuff. But all of that is related to how you can make a nanophotonic glass bead sort of. I don't want to use the word learn. I would rather use the word sort of go through a phase change, so that maybe some of the information is getting, the information of the light beam is getting encoded into the neural network and the into the glass, and then the glass is able to redirect. So again, it's learning from the neural network side, but on the physics side, we wouldn't call it that. But what if we just wanted to have a prediction neural network, right? Like, we didn't want to worry about the learning or anything like that. We just wanted to be able to have a beam of light that sort of fits a curve, that sort of steers around something, like an exponential, right? An exponential decay. So this is what I showed at the end of the last lecture. This is just glass. This is just a glass bookend. Nothing special. Got this for like $5 at a store. All it is a bunch of cut glass, and that's it. The cool thing is that with light, with total internal refraction, you can do a lot of cool stuff with light without the need to have the light respawn back on the nanosecond time scale. I mean, it is, but it's not what's Okay, so normally we talk about the concept of total internal refraction, right? So there's an angle here where I can shine this beam of light, and you can see here, so I'm shining the light in this way, the light's reflecting through the medium and coming out over here, right? And so me moving the angle of the light, you can see how that's changing the angle that's showing up on my hand or the table. Okay, and okay, so one, input matters, frequency, because if I change this, what's going to happen as the light propagates through this? Anybody remember? So how do you determine your refractive index? Hint. Okay, so the frequency matters. We're not going to worry about polarization and all that. But frequency matters and the angle matters, right? So you can see here that I'm basically pointing the laser at myself, and you can see that the laser is actually coming out this way. Okay, so angle matters. Okay, so now the question is there a method that I could do that gets some photons, just some photons, to exit the top or to exit out here? So if I do this, I can actually get, oh, I just had it. Right there. I'm not sure if you saw. It may have been reflecting off of something else. But yeah, there we go. Right there. I'll try to highlight it in the video. So I got the output here. I was pointing the light in through here. And we want it to be a exponential curve, right? Is this an exponential curve? Because the reason I'm covering this is twofold. One, just some ideas about just even curve fitting in science in general, right? And why it's so important that you have to make sure that what you're modeling is actually what the output is. So notice that if I put the laser in through here, it was able to basically do a right angle and come out here. And if all I cared about was what the answer was here for an exponential decay, it doesn't matter. This is what Feynman showed, right? That the light will take all the different paths, and the ensemble average will be the shortest path, right? That's what Feynman proved. But there's times when we actually want the entire length that the photon traveled, right? So we want to make sure that it's correct, because we want to make sure that we're getting this answer, but we're actually getting this answer because of the underlying physics. We don't want the light to, so if I'm trying to do an exponential curve, I should expect more than just one bounce, right? You need a successive amount because that's the whole point behind exponential decay, right? We often forget that that the decay constant is not a constant, right? Because it's the ensemble average, right? That's the whole reason why you have to exponentiate it, because it's proportional to n. As n changes, the lifetime, the mean lifetime. So early on, when you have a whole bunch of your samples, it's the statistics that are changing for exponential decay, right? You're not measuring, in exponential decay, you're not measuring the decay constant. You're measuring the statistics of how that decay constant changes with the population. That's exponential decay, okay? So you're looking for that expectation of value. So So that means that it's not just one thing, it's a successive change. So in the beginning, in the exponential decay, where we're mostly pointing down, the change in the population is going to be very large, right, with a short amount of time. But then as you move along in time, then the change in population, when you have very few, is going to be very few, but with a lot longer time span to get the same number of decays as you did here, right? So what you're actually getting in exponential decay is basically you're looking at how that vector that's pointing in the direction, so thinking about phase space, that's pointing in the direction of the change in population, what you're looking at is how that vector changes with time to be rotated into the time axis. So you start off with the majority of your change in your phase space happening along the carrier concentration, but then over time that is being rotated. There's a certain critical point where the slope is the change in population to the change in time is 1. I'll leave that to you to think about, and we can maybe cover it in a later video. And then, so there's that point where it's 1, and then basically the time axis starts getting stretched out. So if you try to do something like kind of like a PCA, you would have a whole bunch of your dots up on basically the phase space density of your points would be very large at the top of your curve and at the end of your curve on both axes, right? But the dots, but over time, you're going to see that they become fewer and fewer until you get to that critical point, and then they start getting longer and longer on the other axis. And when you convert that to your log scale, that's where you get your straight lines or your semi-log, whichever, however you're plotting it. Basically, decay is that decay constant is about how the phase space is changing over time. You're looking at basically how the topology of that graph is changing. So now, come back here. So we want to make sure that all of that gets considered in our graph. So when I try to fit this to this curve, what I want to do is make sure that this beam of light, see right now it's coming through, and that's basically going through the majority here of the bottom glass, but I want to try to find an angle where right here, this is a good start. So here I can see that the light hits here, hits the first bead, hits the second bead, hits the third bead, and I can actually see some of the light shining on my hand, but it's coming from this one. So you can play around with this angle quite a bright bit, and you can eventually get the light to either come out through this node or throughout the top. And I've got a few images depicting that. We're going to do the same thing with Snell's law in an application. Okay, so we're going to show how you basically can change the angle of your transfer matrix, and that will bend how a signal propagates through a set of glass, thin films. And from that, we'll talk a little bit more about autoencoders and cool stuff like that. But anyway, wanted to give an open demonstration of this, and thank you.